So many of you look like you struggled on quiz 4, so let's go over it, see how to solve all of these problems so that you can do better on the exam coming up. Okay, so first problem, so it's from chapter 4, it's dealing with concentration. So insulin's a hormone that controls the use of glucose in the body. How many grams are required of the solution to make 50 mils of a 0.0037 molar solution? Okay, so when I see this, so what you have to do first of all is recognize anytime you see capital M, that's molarity, and anytime you see molarity, capital M, you should immediately write this as 0.0037 moles of insulin per liter. So you have a moles per liter there, you see 50 mils. If you convert that to liters, so divide by 1,000, so that would be 0.050 liters. Okay, so you have a liter there, you got a liter there. If you just multiply these two numbers together, then liters will cancel and you'll have moles. So that's how you start this, 0.0037 moles of insulin divided by 1 liter, multiplied by the 0.05 liter. So that would give you 0.000185 moles of insulin. But the question asks for how many grams? Well, you're given the molar mass is 5,808 grams per mole. So again, you have mole here, you have mole here. So if you just multiply those two numbers together, moles cancel out, and then you're left with grams, which is what you want. So take that and then multiply by 5,808 grams per mole. It's grams of insulin. So moles cancel and you're left with grams, so times 5,808, and you get 1.07 grams. So that's the answer. Okay, so for the next problem, so 1 mole per liter. So again, you see capital M, you should immediately write that as mole of HCl per 1 liter instead. Okay, so how many mils of stomach acid can be neutralized by 1 antacid tablet? So 500 milligrams, that would be the same thing as 0.500 grams, right? Okay, so you have grams, and you're given the molar mass here, so you have grams there. But you can't just multiply these two numbers together because then you would have grams times grams. So you'd have grams squared divided by mole. So what you have to recognize is you need to invert this number. It's 1 mole over 100 grams. And then you can multiply these two together and grams will cancel out and you'll have moles of calcium carbonate. So 0.500 grams calcium carbonate times 1 mole. CaCO3 per 100 grams. So you have 0.005 moles of CaCO3. And now you have to recognize it's a stoichiometry problem. So you have 0.005 moles of this. So now you have to use molar ratios because we want to figure out HCl. So there's a 1 here, right, and a 1 there. So 1 mole of this needs 1 mole of that to react with. So if you do the conversion, so 1 mole of HCl per 1 mole of CaCO3. So you need the same number of moles of HCl as you have CaCO3, so 0.005 mole of HCl. But then the question asks for how many mils of stomach acid can be neutralized. So we need to convert that moles to a volume, and you do that by using the molarity, because molarity is moles per liter. But here we have moles on top, and molarity is moles on top, so we need to invert the molarity. So we multiply this by 1 liter of HCl over 1 mole, which means you need 0.005 liters. That would neutralize 0.005 liters of the HCl solution. of this stomach solution. But the question asks for how many milliliters, so you need to convert that to milliliters, so times 1,000 milliliters per liter. So that would be 5 mils. So that's the answer. Okay, so this one you have 2 molar solution. So what does that mean? 2 moles of magnesium chloride per 1 liter. And so let's say, so you had 600 mils of it. Okay, so you forgot to cap the flask, so overnight 300 mils evaporated. Okay, so so half the volume evaporated. So we can make this calculation easier. So 2.0 capital M means 2.0 moles per liter. So if half of the volume evaporates, but magnesium chloride is a salt, it does not evaporate. So you still have 2 moles of the MgCl2, but now the volume is halved. So now it's 0.5 liters. And if you calculate that out, you would see that it's 4 molar, right? So if you decrease the volume by 2, the molarity doubles. So that would be the answer. Okay, so in this case, again, you have a 2 molar solution. 2 moles of MgCl2 in 1 liter is what that means. So I tell you have 600 mils, but you can make the math easier. Just as, what if you had a liter? Then you would have 2 moles of magnesium chloride. And in this case, it tells you, so you take this and pour it into another flask. Let's see, total volume. So you take half of this. So if you take 1/2 of this solution and put it in another flask, and then add another 300 mils, so basically you're doubling the volume, right? So if you double the volume, so you would go from 2 moles, however you want to look at this problem. If you double the volume, 2 moles, now you have 2 liters, then the molarity would be 1.0 molar, right? Of course, in this question, it's telling you that you have 600 mils and it's 2 molar. And if you took out 300 mils, it's still 2 molar, and then put another 300 mils in. So basically what you've done is you've simply doubled the volume. So that's why I say you could simply take that and think of it like that. If you simply double the volume, you have the molarity. So the answer here would be a 1 molar solution. Okay, so in this case, if you have a 2 molar solution, so 2 moles per 1 liter, and you spill half of it on the floor, so now there would only be 500 mils here, and there would be 500 mils here. So you spilled half of the liquid, but you also spilled half of the magnesium chloride as well. So that means there would be 1 mole of magnesium chloride left in the flask, and there would be 1 mole of magnesium chloride on the floor. So the concentration doesn't change, right? You have not changed the ratio of magnesium chloride to liquid. It's just that half of it's on the floor, but the molarity is still the same. So you don't really need to do any math to solve those type of problems. You can just think about them, right? If you keep the solid solute the same and half the volume, the concentration doubles. If you keep the salt, so number 4, if you keep the solid solute magnesium chloride the same but double the volume, then the concentration is in half. And if you don't change the ratio at all, if you keep the moles of magnesium chloride to the volume ratio the same, then the concentration stays the same. It's just that half of it's on the floor and half of it's in the flask still. Okay, so this one's a lot harder problem. So this one you got to work through. Okay, so we have 2 mole of magnesium chloride per 1 liter of solution. Again, that's what the 2.0 molar means. But you only have 600 mils, so you have 0.600 liters. So if you multiply those two numbers together, liters cancel out. And so that means in this flask, there is really 1.2 moles of magnesium chloride. So in that flask, there's 1.2 mole of MgCl2. And now let's convert that to grams. So you need the molar mass of magnesium chloride to solve this. So you need a periodic table. Magnesium's 24.3050, chlorine's 35.4527, and there's 2 of them. Okay, so that's 95.21 grams per mole. So let's convert this mole here to grams. So 95.21 grams in 1 mole. Okay, so in this flask then there's 11.425 grams of magnesium chloride. And then I tell you, you add another 10.5 grams. So let's take that and add 10.5 grams to it. So now you have 12, oh, I think I wrote this answer wrong. Let me do this, yeah, 95.21 times 1.2, sorry, 114.25. And then you add 10.5 grams to that. So now then in this flask, there's 124.75 grams of magnesium chloride. So let's convert that back to moles. So use our molar mass again that you calculated earlier. So 1 mole is 95.21 grams. Oh, that's right, it's a mole. So you have 1.31 moles. So this 124.75 grams is the same thing as 1.31 mole of MgCl2. So you take that, pour it into this flask. So there's 1.31 moles in here, and then you dilute to the 1 liter mark. So if you want to convert to molarity, it's the moles divided by the volume. It's 1 liter. So the molarity is 1.31 molar. Right, so that's the answer. So that was definitely a little bit harder problem. It required you to think a lot more to work your way through all of the steps in this, what's going on. Okay, number 7, what's the oxidation number of manganese in each of the following compounds? Okay, so MnO4. And again, to solve these problems, you have to know the charges on these polyatomic ions. You have to know that our permanganate is MnO4 -1. And then you have to know that oxygen is always -2 unless it's O2 or H2O2. So that would give you 8 negatives. And so manganese must balance that to -1. So manganese must be +7. +7 and -8 gives you -1. So if you didn't remember permanganate's -1, you could have solved this from barium because barium is group 2 in the periodic table. So you know barium's +2, and there's 2 permanganates. Since there's 2 of these, and each one must be -1, that gives you 2 negatives to cancel out the +2 from barium. So if you didn't remember permanganate was -1, you could have figured it out if you recognized barium was +2. Right, so in this case then barium, MnO4, 2, so that's +2, so that's 2 positives. That's +7, there's 2 of them, so that's 14 positives. Each oxygen's -2. And there's 8 oxygen, each oxygen's -2. And there's 8 oxygens, so that's 16 negatives, so that gives you a sum of 0 for all of the atoms together. Okay, so for MnF3, if you know that fluorine is -1, then manganese must be +3 to cancel all 3 of the fluorines out. So manganese +3 there. And so for this one, you have to know that the charge on NO3. If you don't know the charge on NO3, you can't solve this problem. You have to know it's -1. And so there's 2 of them. So that means manganese must be +2. Right, so in this problem, manganese, so there's 2 of these. So oxygen's -2, there's 6 oxygens, so that would be 12 negatives from the oxygens. And since NO3 is -1, so 6 negative from oxygen, that means nitrogen must be +5. So that +5 and -6 gives you -1. So each nitrogen's +5, there's 2 nitrogens, so that would give you 10 positives. So manganese must be +2 since there's only 1 manganese, and all of those would equal 0. Okay, so for MnO2, this one's a lot easier. Oxygen's -2, that's 4 negatives, so manganese must be +4 to balance that out to 0. So manganese +4 there. Okay, so this is a dilution problem. You have 0.35 molar and you have 12.4 molar and you want to make 0.35 molar, so that's a dilution. So that means you need this equation, M1V1 equals M2V2. Okay, so you want to make 2 liters of this. Okay, so M1 is the 12.4 molar that you start with. You need to calculate how many liters of that you need to dilute, so X. And you want to make 0.35 mole per liter, and you want to make 2 liters. So solve for X. So 0.35 times 2 divided by 12.4, and this is going to give you liters as the answer, right? Because of the units here. And the question asks for milliliters, so once you get the answer, you're going to have to divide it by 1,000 to convert to milliliters. So 0.35 times 2 divided by 12.4 gives you 0.0565 liters. So 1, 2, 3. Move the decimal point 3 places to the right, so 56.5 milliliters. So that's the answer. Okay, so which is the base in the following reaction? So can't solve this problem if you don't know the definitions. So what's an acid is a hydrogen donor. What's a base is a hydrogen or proton acceptor. Okay, so this molecule, H2PO4, becomes that. So that lost a hydrogen. That means that's an acid. And H2O becomes H3O plus. That means that gained a hydrogen, so that's the base. So H2O liquid is the base. Okay, so according to Bronsted-Lowry, an acid is you just got to know the definition, is a proton donor. Okay, so in this problem above, for example, H2PO4 so we said this is the acid, this is the base. So then if we consider the reverse reaction, so H3O plus becomes H2O, so that lost a hydrogen, so that means this is an acid. and then this gains a hydrogen, so that means this is a base. So if you notice the conjugate acid-base pairs, so H2PO4 minus and HPO4 2 minus, how many hydrogens they differ in? 1. And the other pair is H2O and H3O plus. So H2O is a base, H3O plus is its conjugate acid, right? So these on the right-hand side are usually called the conjugate base and conjugate acid. So how many hydrogens do they differ in? 1. So you just have to compare. These differ by 1 hydrogen, these differ by 1 hydrogen, these differ by 1 hydrogen, those differ by 1 hydrogen, these differ by 2 hydrogens. That's not a right acid conjugate acid base pair. So that would have been the answer. Okay, so identify the Bronsted-Lowry base. So NH3 becomes NH4, so that gains a hydrogen. And so bromine basically loses the hydrogen to NH3. So NH3 gains a hydrogen, so that's going to be the base. And it's a base because bases are proton acceptors. So not that is a base because it's a proton acceptor. So you should be able to, just based on definition, eliminate 2 of these immediately. So bases are proton acceptors. That means it's either that or it's that. And so you just then have to identify which one of these gained hydrogen in the process. Did HBr gain a hydrogen or did NH3? Okay, so this one, another chapter 4 problem. All of these so far from chapter 4. So you're asked to write an ionic equation. Start from this equation. So you have to recognize that, first of all, that's barium's the cation, and what charge does it like to be? It likes to be +2. So, and then you have to recognize that it's not Ba. So you have to recognize Ba is +2, and you have to recognize it's not Cl2 negative. CO2, it's 2 Cl negative 1s. Right, that would balance the +2 on barium. So it's not that, no CO2 negatives, right? And so that means you're left with choosing between that or that. And then you have to recognize here for magnesium sulfate, when this splits up, when it dissolves in solution, it's going to be a magnesium 2+ cation. And the SO4 stays together. It's one of those polyatomic ions that you had to have memorized. So, you know, students all the time want to break this up to sulfur and oxygen, but that's not what you do. So that's how you know to eliminate that. So the correct answer is this one. Okay, and then if you want to write the net ionic equation, so the net ionic equation only shows things that change. So if we go back to this equation, so really you have to come up with the correct ionic equation first. If you don't come up with the correct ionic equation, you can't come up with the correct net ionic equation. So what changes? Well, what did not change? Cl minus did not change. 2 Cl minus on the left and the right. And a magnesium 2+ on the left and the right of the arrow, so you can cancel those out. Barium changed and sulfate changed. All right, so that would be the net ionic equation. So barium and sulfate changed because they came together to make a solid compound. And then the spectator ions are the things that don't change. So what did not change in this equation is the things we canceled out, the magnesium and the chloride. So Cl minus and magnesium 2+ are the 2 spectator ions. Okay, so what are the Bronsted-Lowry bases in this reaction? So again, so this lost a hydrogen going forward, and Cn minus gained a hydrogen. So this would be a base, and this would be an acid. And then if you consider the reverse reaction, H2PO4 becomes HPO4 becomes H2PO4, so that gained a hydrogen, so that's an acid. And HCN becomes Cn minus, so that lost a hydrogen, so this is a base. So there you go, there's your two bases. Whoa. No. I got that wrong. Let's fix this. Let's try again. Okay, there we go. This gained a hydrogen. Oh my goodness, I got this all wrong. Let's just start this one over. Try again. H2PO4 goes to HPO4. That lost a hydrogen, that's an acid. Cn minus goes to HCN, that gains a hydrogen, that's a base. For the reverse, HPO4 becomes H2PO4, that gains a hydrogen, that's a base. And HCN becomes Cn minus, that lost a hydrogen, that's an acid. So now your two bases are Cn minus and HPO4 2 minus, so right there. Okay, more oxidation numbers. So fluorine's -1. There's 5 of them, so that's 5 negatives. There's only 1 phosphorus, so it must be +5 to make that sum to 0. Oxygen's always -2, so that's easy, unless it's O2 by itself, right? There's a difference between CO2 and O2. This O2 is 0, this O2 is -2 because it's bonded to carbon. So if oxygen's -2, that's 4 negatives, so that means carbon must be +4 to balance that out to 0 because there's only 1 carbon. So this oxygen's -2, that's 4 negatives. It must sum. It must sum to -1, so nitrogen must be +3. So +3 and -4 gives you -1. Okay, lithium's a group 1 metal. Group 1 metals always like to be +1. Sulfate has a net charge of -2, so if oxygen's -2, that's 8 negatives. There's only 1 sulfur, so sulfur must be +6. +6 and -8 gives you -2, so sulfur's +6. Okay, this one, platinum. If you know that, you have to know the charge on nitrate. If you don't know the charge on nitrate, you can't do this. Nitrate's -1. There's 4 of them, so that's 4 negatives. There's only 1 platinum to balance that to 0, so platinum must be +4. And here, Br2, that's pure element, so oxidation number of 0. Okay, so now you got to know some definitions. What's oxidation, what's reduction, what's an oxidizing agent, what's a reducing agent. If you don't know those definitions, you can't do this. If you don't know how to assign oxidation numbers, you can't do these problems. Okay, so that's pure copper, so that's 0. That's pure chlorine, so that's oxidation number of 0. That's +1, so its oxidation number is +1. And that's -1, so its oxidation number is -1. Okay, so how did copper go from being 0 to +1? By losing 1 electron. And how did chlorine go from being 0 to -1? By gaining 1 electron. Okay, so what is oxidized? So that is the species. If it's oxidized, that means it lost electrons. So which one lost electrons? So which species is oxidation is loss, right? The acronym oil rig. So oxidation is loss. So copper solid was oxidized. Okay, so the next question, it's the same reaction. So which species is reduced? That will be the one that gains electron, right? Reduction is gain of electrons. So CO2 gained electrons, so it was reduced. Okay, and in this one, again, to solve this, you have to do oxidation numbers first. Manganese is +7. Oxygen's -2, right? That's 8 negatives, and +7 gives you a net -1. And oxygen's -2, you have to have a net -1, so that's 4 negatives. So nitrogen must be +3. Okay, so nitrogen's +3, manganese is +7, and over here manganese is +4, and nitrogen's +5. Right, because oxygen's -2, and that's 6 negatives, and +5 and -6 gives you a net -1. Okay, so how did manganese go from being +7 to +4? By losing 3 electrons. How did nitrogen go from being +7 to +4 means it gained 3 electrons, right? +3 to +5 means it lost 2 electrons. Okay, so what is the reducing agent? That is the species that loses electrons. So what lost electrons in this case? That right there, lost 2 electrons, so that would be NO2 minus, would be the reducing agent. And so same reaction, what's the oxidizing agent? Well, that's opposite. That's the species that gains electrons. So manganese went from +7 to +4 by gaining 3 electrons. That means it's the oxidizing agent. Okay. So again, to work those problems, you have to know how to assign oxidation numbers, and you have to know the definitions. Otherwise, you cannot solve those problems. And so for those of you who go on to Chem 1312, there'll be an entire chapter over this type of chemistry. So if you learn it really well now, it'll be much easier for you in Chem 1312. Okay, and so for writing half reactions, so again, it's oxidation reduction. So zinc to zinc 2+, that means how does it go from being 0 charge to +2? By losing 2 electrons. And how does chromium go from being +3 to 0? By gaining 3 electrons. Okay, so zinc, so one half reaction is zinc 0 goes to zinc 2+ plus 2 electrons. It lost 2 electrons, so electrons are right on the right of the arrow. And chromium 3+ gains 3 electrons, so that means you write them on the left of the arrow. Goes to chromium 0. So you're looking for one of those 2 reactions. That's your 2 half reactions. And so zinc to zinc 2 plus 2 electrons, that's one of them. And your other half reaction is not shown. It's not one of the choices. Okay, so for this one, zinc, another oxidation reduction, tan goes to tan2 by losing 2 electrons. Silver goes from +1 to 0 by gaining 1 electron. So what is the reduction reaction? The reduction means reduction is gain, no, reduction is loss. OREG. Reduction is gain. So I have to think about it all the time too, because the definitions get twisted in my head. So reduction is gain, so you're looking for the reaction that gains electrons, so that would be silver +1 electron. Go to silver 0, so that's your reduction reaction. Okay, and in these chapters we're into chapter 12. So highest viscosity is going to be the one that's going to be the one with most surface area, which is going to be this one. Right, that's going to have the maximum van der Waals contact, so those molecules are not going to want to slide by each other. They're going to stick to each other, and so they're going to be very viscous. They're not going to flow very well. And so same thing here, highest viscosity, so we're looking for the most surface area, which will be that one. Okay, most water is soluble. So basically you're looking, water is very polar, so most polar. So you're looking for the most polar molecule. So for this one, that's going to be B, right? B is more polar than A because oxygen's partial negative, carbon's partial positive. That molecule has a dipole moment, the other molecule doesn't. So B is more polar than A. So B. And this one, they both have an OH, so that's a wash. That's the polar part of the molecule. So then you're looking at this part of the molecule is hydrophobic. So you're looking for the molecule that is the least hydrophobic in this case, which is going to be molecule A because it's got a shorter carbon chain. Okay, so in number C, so in C, comparing these two molecules, so they both have a 4-carbon chain, but what is significant is this molecule B has an OH, and the significance of that is that's very polar, right? That can hydrogen bond to water. And so that's going to make it more water soluble because it can make more hydrogen bonds to water. So it can both make a hydrogen bond to oxygen of water and to hydrogen of water. So for molecule, so for D, this molecule has a partial negative oxygen, so it can make a hydrogen bond to water, so that's going to make it more water soluble. So A. So for E, this part of the molecule is the same. So that's the only polar part of the molecule. Since the polar part of the molecule is the same, then you're going to look at the carbon chain and find the one that's the least hydrophobic. Well, this has 4 carbons. 2 carbons there and 2 carbons here, and this has 1 carbon here and 2 carbons here, so 3 carbons is less hydrophobic than 4 carbons, so A is going to be more water soluble. And then for F, well, this oxygen can hydrogen bond to water, but this oxygen can hydrogen bond to water, and the hydrogen can hydrogen bond to water. So you can make more hydrogen bonds to water, plus there's only 2 carbons compared to 2 carbons and 2 carbons, so there's less hydrophobic, so B is way more water soluble than A. Okay, so in terms of boiling point, let's see, so what you're basically looking here is increased polarity, increases boiling point, and increase in carbon chain increases boiling point, right? Whereas for here, for water solubility, decrease in carbon chain increases H2O solubility. Okay, so this molecule is more polar. It's going to have a higher boiling point. It's got a dipole, the other molecule does not. The OH is a wash, so then you're looking at the carbon chain. This has got more carbon chain, so that's going to have a higher boiling point. So B is a higher boiling point. For C, this is more polar. It can make hydrogen bonds to itself. Right, 2 of those molecules can hydrogen bond to each other, and so that's going to increase its boiling point. So B is going to have the highest boiling point. And for D, this molecule is more polar, so it's going to have the higher boiling point. Right, that molecule has a dipole. Can't hydrogen bond to itself, but it does have a dipole. And for D, again, this part of the molecule is comparable, so then you're just looking at the carbon chain. Which one has a longer carbon chain is B, so that's a higher boiling point. And for A, so you're comparing that part of the molecule to that part of the molecule. Anytime you have an OH, it can hydrogen bond to itself, so that's going to increase its boiling point, so B has a higher boiling point. Okay, so 31, which can make hydrogen bonds? So to make hydrogen bond, you need 2 things, right? You need a partial positive hydrogen. How do you get a partial positive hydrogen? It'd be attached to a very electronegative atom. So if you compare the 2 molecules, the only hydrogen that is partial positive is that one right there. So that's the hydrogen that can make a hydrogen bond. But what does it make a hydrogen bond to? The second thing that you need is an atom with a lone pair of electrons. All right, so this is not gonna, so that's not, you can't hydrogen bond between 2 hydrogens. And that hydrogen, well, that hydrogen's not partial positive. These hydrogens are not partial positive because they're not, they're attached to oxygen, or carbon, they're not attached to a very electronegative atom. So this is the correct answer. All right, you have a partial positive hydrogen because it's attached to a very electronegative atom, oxygen, and you have a partial negative atom that hydrogen is going to be attracted to. Okay, and so the other one have problems either. Others either have no partial positive hydrogen or not an H bond to partial negative atom with lone pair of electrons. Okay, so for the next set of questions, and I know for you they were scrambled, but on the test they're all in a logical order here to me. So you're looking for intermolecular attractions. So there's hydrogen bonding, there's dipole-dipole, and there's ion dipole, and there's van der Waals, which is the same thing as London dispersion forces, which is the same thing as induced dipole, induced dipole. Right, I say that because that allows you to eliminate these two right away. Those are not possible choices because the other four are the only ones that are intermolecular attractions. Okay, so to make hydrogen bonds, you need a partial positive hydrogen. There's obviously no hydrogens in Cl2 or F2, so you can't make hydrogen bonds. There's no dipole in the molecule, so there's no dipole-dipole attraction. There's not an ion because an ion means something charged, right? Like an M plus or something negative, like means a cation or anion. There's no ion, so it can't be that. The only thing left is van der Waals attractions. And for this one, this molecule right here has a partial positive hydrogen. That oxygen's partial negative with a lone pair. They can make hydrogen bonds. That's what it's going to do. All right, it's going to make hydrogen. So which of these are the strongest? These are the strongest. Well, that and ion dipole. And these two are the weakest. But this is the weakest. So given if they can do more than one, you're always going to go with the one that's the strongest, is the most important. And in this case, hydrogen bonding. Okay, these two molecules, that's an ion, right? Anything that's positive is a cation. So you pretty much have the answer right there. It's an ion dipole. All right, does this molecule have a dipole? Yes, because oxygen's partial negative, carbon's partial positive. So it's pulling electrons that way, and the net is that way. So what this would look like is this molecule would orientate itself with the partial negative oxygen towards the lithium cation, and you have an ion dipole attraction. Okay, so for this one, that hydrogen is not partial positive because it's not attached to an oxygen or a fluorine or chlorine or nitrogen, something very electronegative, right? It's attached to carbon, and the difference in electronegativity is 0.35, which is less than the threshold of 0.4, so it's nonpolar. So that's a nonpolar covalent bond between the C and the H. So if you remember, in those cases like that, we ignore partial positive and partial negative. So no charge on hydrogen. So hydrogen bonding's gone. Fusion's not an option. There is no ion, so it can't be an ion dipole. Van der Waals and induced dipole, those are the same thing. So do these molecules have dipoles? Yes, that's partial positive, that's partial negative. That molecule has a dipole. Carbon's partial positive, nitrogen's partial negative. That molecule has a dipole. This will be a dipole-dipole attraction. Okay, so for this one, so lithium is a cation, so that's an ion. So we're looking for an ion dipole attraction. What's a positive going to be attracted to? It's going to be attracted to a negative. So you want to align the partial negative oxygen with the positive lithium. So that's the only one that makes sense, right? Because this hydrogen's partial positive. You're not going to have two positives attracted to each other. So all of C, D, and E has positive bonded to positive. That's bad. And here, the dipole's pointing in the wrong direction. It needs to point towards the cation. Okay, so A is the choice, and that's called an ion dipole attraction. 37. Okay, so last one. So the lithium nitrate, so now the other half of this, so what is the nitrate going to look like in water? Well, so nitrate, that oxygen is partial negative, these two oxygens are full negative. So negatives are going to be attracted to positives. So what's positive in water is the hydrogens. So you're just looking for a hydrogen that's bonded, hydrogen bonded to oxygen. So that doesn't make sense to have a partial negative oxygen near another oxygen that's negative. This is the one, partial positive hydrogen near a negative oxygen. That would be an attractive interaction. So that's the answer, B. All of the other ones, you have a partial negative atom near a partial negative, that's bad. Here you have a full negative atom near a partial negative atom, that's bad. Here you have a partial positive hydrogen near a partial positive nitrogen, that's bad, right? You're looking for, in all of these, you're looking for something that will be attractive. A positive attracted to a negative. So the only answer that's reasonable is B. And what do you call that type of attraction? That's hydrogen bonding. Okay.